Welcome to a new test and teardown video. This time it's another radiometer. This big thing is from the start of 1960. It's a capacitance bridge, so it can measure the value of capacitors. So the type number is CMB1C for the capacitor bridge, and the unit actually consists of a sub-unit called the oscillator amplifier, and that one got its own type number OSF2B. And it should be possible to separate these two units, not by the case as you can see here, but you should be able to unscrew this and then unplug it. So we've got some interconnects here, so it should be fairly easy to upgrade the oscillator amplifier or the capacitor bridge. If we look at the range, it is absolutely amazing. So we got, this is multiply times 10 picofarad. So this is 10, 20 and so on, right? So this is 0, and it's the same with 100 and 1 nanofarad. So multiply by 10 nanofarad. Okay, fantastic, right? But we also got here is multiply by 1, right? So then this is the truth. And then 1, because all those are in 0 now. So if I find my peak at exactly 1 here, this is the picofarad. So 1 is now 1, right? So that is 1 picofarad. Well, look at that. Now it's 0.1 picofarad. Or now it is 0.01 picofarad. But what you can do is you can actually go 1/10 of that. Look at that. So if your peak is right here, you are now reading 0.001. That is crazy. I actually think there is a 0 more in the specification sheet. So let's just find the specification sheet and have a little look what they claim is possible, because I think that is actually a little bit better than that. Of course, we can ground this detector or free. I don't know exactly what that is. So that's of course CX, and then we got the power factor. And how sharp is the power factor? Here we don't know exactly what it is. I think this is something to do with the measuring the Q factor of the capacitor. And here we can, this is of course the oscillator amplifier, so we can give more or less output. That has of course something to do with the detector. So you can set up the detector for phones or for the indicator. And then you can adjust how much amplifier gain you want. I've spent a full hour, I guess, on cleaning this. So it's, as you can see here, it is really, really nice and clean all over the place. And it was definitely not looking like this when I got it. I got it at a flea market, really, really cheap. But look at that. There was an OK marker here on the top, so I got big expectations. What I think I need to do, definitely always on old stuff like this, let's open and perform a deep visual inspection before I first power up. And this is all there is to it. The oscillator amplifier is of course the section with all the valves, all the active kind of stuff. and here is the output, and here is the input, and that is all. This goes into the detector, and this goes out to the bridge. And here is also our mains entry, the on-off switch, mains transformer. It drives the, what is that, an EM3? I would definitely guess so. Yes, no, it's an EM34. Oh, I love those magic eyes. I really hope that one works. Otherwise, I think I got exactly that model on stock as well. EF86, a very, very famous pentode. Oh, we got more EF86. ECC83, a dual triode, and an EL83. Okay, that is really all there is to it. I mean, so this is the oscillator. A output transformer drives the output, and really not a lot. Oopsie doopsie. Let's see what we got here on the back. I didn't really find any leaked capacitors. They all look quite alright. I really like the layout here. It is so nice and clean and beautiful. Selenium rectifier for the high voltage, just some resistors and then filters and all that kind of stuff. See, positive goes directly to a capacitor, and then via a resistor to the capacitor. Oh, via another resistor to another capacitor. Yeah, man, let's do the filtering. Yeah, that's more or less the entire schematic, really. You can just read it out here like that. Super easy. So, oh, I have to be careful. The rest of the bridge is here on the floor. And as you can see, there is a wall in between the two units. Ooh, there's a dead spider. And then, yes, I can lift up the capacitor bridge. There's not a lot to say about the bridge before I open it. But I really would like to show you the... Oh, we have a little challenge with the light. It is completely dark down there. I am so sorry about that. So that will be our ground. Oh, there's a... Why is it made like that? That's a little bit interesting. And of course the other signals, they're very good shielded. But it's only 1 kilohertz. And this will be the power factor multiplier. Power resistors here and all that. Oh yeah, look at that. So this one is of course our capacitor bridge adjustments. Look at that, they did this double just so there's no, like when you grab this and do the bend the whole thing, right? You really want this to be mechanically isolated from this entire high Q circuit. And also here is our zero adjustment. You really want to see a little cool detail. So this screw here, lift this plate away from that plate, and that is our capacitor adjustment. Oh, that is nice. Yeah, so I have to take away the different it is too heavy to lift in one hand. Well, we definitely want to look in here, right? We are now inside the capacitor bridge. And what do I find here? Some really, really nice and cute capacitors. Look at those three. They look like mica condenser. Serial number HW Sullivan, London. And look at the value on that one. And this is absolute value, right? And it goes on and on. We got a lot of zeros on that one as well. Oh, and this is microfarad, 0. And I don't know what, how many zeros we got. 4 zeros and then 97. Lovely, lovely, beautiful capacitors. And then they go in series with some other capacitors here, so we can super fine tune. And up here is this is actually the bottom right. This is the capacitor you use for the measurement, and it's actually just going around and around, by the way. Here we go. That will be the multipliers, if I am not mistaken. Yes. So this is the 1, 10, and no, that is wrong. This is 10 picofarad per step, right? 101 nanofarad per step, and all this is just resistors. So that means, because this is the resistor side, you can do whatever you want, right? This is totally not critical. And this way you can just wire all this like this. There is no crosstalk, there is no nothing. Ha! It is low impedance resistors, as you see here. Isn't that just cute? I really love the fact that all this internal metal here is shielded and isolated from the front. If you see down here, there's actually a plastic isolator on all of them, all those screws, and also that one here, you can see that they're isolated, and I actually don't understand why there is this shield around it. So that means the radiation or the pollution from that screw is not going to couple to anything, because it couples better to this piece of metal. I mean, really? Amazing. Oops, my camera here is falling. I'm not so lucky. I think we are ready to do the first power up, and I feel lucky. So let's just crank on mains, and we got light. 50, 40, 30 watts, and yeah, look, we got green. Oh, this one is too bright. Let's see if there's, yeah, it's definitely responding to the oscillator output. And then we got some amplifier gain. Yeah, see? So I can amplify. I mean, definitely. We got the oscillator working. See? And I can crank this down and then give it more from the oscillator, and then, yeah. It's funny, it's not going all the way down, right? Flat. Why is it? There is something wrong with the Magic Eye DC. There's a capacitor here in this system, and as you can see here, it's already half the way deflected. So we're only using this little tiny bit of deflection you see here, right? Only this. Normally they open a lot more, right? So there is something I want to have a look at. And you can of course change the... Ah, that is cute. So it turns off. And the lamp even blinks when I turn on and off the magic eye. So that is 24 watts it is using right now. So let's turn this off and it's still 24 watts. Okay, so it's only the high voltage I turn off. And since 99.9% of the power is in the filament, we don't see any difference in power usage. Of course not on the mains side. But I definitely think it works. I will see if I can find a schematic and maybe fix this deflection kind of system here. Is not super perfect. Haha, I was right about my assumptions about the deflection. Let's perform a little bit test on this. This is the EM34 Magic Eye, and this is the grid voltage, DC voltage on the grid. This is the standard setup with 1 mega ohm resistors, exactly like this schematic I will put in here so you can see this. Let's start to go positive. So this is 100. Why is it doing that? So this is positive, and this opens up the eye. As you can see here, it's supposed to be 0, like that. If I remove the grid from my power supply, look at that, then it goes negative, as you see here, and this is because of the current in the grid. So now I connected it again to the power supply and we have 0 volts. And this is like the data sheet, they only talk about the grid voltages, not the grid currents. Okay, let's reverse the 2 connections to my power supply. So now I will go negative. Now I'll see what happens with the EM34 with negative voltages. You see the 2 different parts of the eye now at 1.8. This part is now touching, but the other part up here is still, there's still a little bit more to go. So let's crank up the voltage until the other part here is closed. That is at -7, something like that, right? So that is definitely how an EM34 works with DC voltages, and I strongly recommend using DC voltages because AC voltages will only make this go more blurry. So you're definitely supposed to come with a DC voltage. Let's look at the output of this oscillator. I just connected a scope here on the output, and I can't show you exactly what I'm doing, but I'm playing around with the oscillator output here. Let's look at the scope at the same time. So this is 50 volts per division. I mean, really? Did I set all this correct? Yes, a probe is in times 10, and my probe is in times 10, definitely. So that is 100 volt peak. And I am not even full. So let's give it a little bit more hammer here. So this is 8, 9. Ooh, now we can hear the tone, and there's still a lot more to give. Holy. So let's look how the curves look. If I crank down the signal, it's going to look a lot better. And this is in 5. So the output here is definitely very, very much logarithmic, just so you know. And the numbers here is from 0 to 10, but that is definitely not how it is. The frequency is 970 Hertz, so it's not exactly 1 kilohertz, and that is of course very, very important for this to be able to measure the correct capacitor values. So I bet that one is the frequency alignment. I would assume I need to play with that. But what if the other parts of the circuits is carefully calibrated to measure the right value with a wrong oscillator frequency? That is something that could be interesting to figure out. So my point is, I don't calibrate anything here before I've seen how the bridge react. So if we look at the schematic again, this switch here is actually both disconnecting the high voltage, that is the red wire on the other side that goes up here, and the high voltage goes to those resistors and all that kind of stuff. But here is the green wire, that is the grid, and we had this 1 meg resistor on the grid to ground, but I changed this to 100k, and I can easily do that because the series capacitor is 100 nanofarad, and the source impedance of the tube amplifier is 10k. So that means this should definitely not change the level or the frequency range of this coupling. So with 100k as the grid discharge, look at that. Now I got much better deflection range, and it's still working quite alright. They're still doing this a little bit wrong with their feeding AC in here, and that means it makes a unfocused picture. It's actually quite obvious. If I do it like this and have a look here below, let me see if I can, yeah, like that. See, it is unfocused, blurry, because it's AC. If I added a diode to rectify the signal from the amplifier tube, I will get a nice sharp picture, just like I showed with a DC voltage. So see another little thing here. This is in AC, and I connected the ground of the voltmeter to earth. Let's measure to the chassis 118 volts. This is enough to tickle a little bit in the fingers, especially when you're touching anything here that's grounded. And this is actually because of dirt in the connector. So my connector that was supposed to be grounded is not grounded. Let me turn this off and let's pull this out. So this one is supposed to be grounded and have a good, nice chassis connection here, but it's dirty down there, so there's no connection. Oh, this is bad. It was not dirty in the connector. You see what had happened? If I only bothered to look more careful. Look at that. This one is not a correct earth model. Damn it. I need to change this because this is totally not safe. Oh, I think I need to show you this. Look now how nice and sharp the deflection is here when I move the input here. And this is of course a 1 kilohertz that I amplify and all that kind of stuff, and now it's just nice and sharp. What I've done is pretty simple. I just took a diode and a capacitor and a resistor, and then it is nice DC to the grid. And now you get a nice and sharp picture. That is how it should be. So now the unit is assembled, and let's try and play with a capacitor. I just know this is a 100 picofarad capacitor, so it's a little bit cheating. So I put this for 0, 0, and 10 times 10. and I am in the magnifier 1, and here is my fine tune. So let's try and dial this while we're looking at the magic eye. See? Oops, let me turn off the light a little bit like that. See? Ooh. So if this is, I go for the maximum, right? I don't know if it's easy to see what I'm doing here. Right there, right? So this is times 1 picofarad, right? So, and here's our 100. But I think this is over 10. So it's 110, right? I don't understand exactly that. It should have been about here, but it's not. So there's definitely a little bit of offset in that. So let's try and take the capacitor and see what it really is. So here we go. So it's 100 and almost 101, right? And I read it. 110. So it's a little bit off, but okay, for 60 years, I mean, it's not that bad, is it? I've also been trying to play a little bit with the power factor and how much I get here and all that, and I get the highest kind of Q, or the highest kind of response. Oh yeah, okay, I don't get any response now because I removed the capacitor. Surely enough, that is how it works. So here is 1 nanofarad, and again I select this one as 0, but I select times, so this is 10 times 100, right? So this is 1 nanofarad, and then I can play around with this one, and then I look, see? Here we go. And this way you can find the peak of that one. So it's 100 and a little bit more than 1 nanofarad. So I really believe this old and fantastic unit works. So I think that was more or less what I wanted to show you guys. And thank you very much for watching. See you again tomorrow.